It's the truth. Okay, audio systems. So looking at PA systems. Right, okay. First thing you need to know with PA system block diagram is you need to know the block diagram. Okay, I'm not going to keep going over it, but just learn it yourselves. So here we go. We have the input sources. So these could be microphones, keyboards, synthesizers, DJ mixing desks, whatever you like. But effectively there's two different types. There's ones that are at what we call a line level, which could be something like an electronic keyboard, synthesizers, CD player, anything that's got quite a high voltage output are called line level, and then the ones that are much weaker, called microphone level ones, have a much lower voltage going into the preamp. They also have a much higher impedance as well. So we have different input sources. We have to make sure that they're all going to get mixed together. So we need preamplifiers to bump up the voltages so they're all a similar voltage range, so that we get a good mix when it goes into the mixer. Okay. First, what I would do with this, Matt, have you got the posters? Oh, you've got yours there, yeah. Okay, first thing we need to know about is impedance matching. The important thing to realise is when we're looking at audio signals, we're talking about voltages. Okay? We don't want current, because current will produce heat, which produces noise, and also it overloads each stage. Things like tone controls don't want to be delivering a lot of current. It affects their ability to boost and cut the tone. So we want to maximise the voltage transfer all the way down the chain until we get very close to the end. The only bit where we want to maximise current is here. So for the rest of it, we're maximising voltage. And to do that, we need to effectively look at it. When the voltage goes from one stage to another, we can look at it a bit like a potential divider. We have the output impedance represented by a resistor of a block, and then the input impedance of the next block along. Now these aren't actually resistors within the blocks, these are the natural impedances of the equipment. So a microphone, for instance, has a high input impedance. That means that we need the preamp here to have an even bigger input impedance, otherwise we'd lose some of the voltage. For instance, if both of these had the same impedance, then half of the voltage would be lost, because it's like a potential divider with two resistors that are equal. So the only way to make it so we get the maximum transferred is, in general, to maximise voltage transfer from one subsystem to the next, the input impedance of the second subsystem should be much larger than the output impedance of the first one. So that one needs to be much bigger than that one. That means then, if you think about it as a potential divider, if you've got a big resistor on the bottom and a much lower value resistor on the top, the output voltage is pretty close to what the power supply is. Okay? So in this way, we don't lose voltage as we're going down the chain. If that isn't possible, if you have a very high impedance source and you want to match it, we can actually use an op-amp as what we call a voltage follower. And effectively it's just a non-inverting amp without the feedback resistors and without the input resistor. That effectively gives it a gain of 1, because it's 1 plus RF over Rin. And if RF is 0 and R1 is infinite, then we're just left with a gain of 1. That means this has a very high input impedance and a low output impedance, so we can put it between two stages to match the impedances. And you just need to know the circuit, you need to know how to draw that. and explain that that's high impedance and that's low output impedance.
Which one's high? The input is high impedance.
Yeah, because that's high input and low output, so that means you could put it between here and here, and you'd end up making sure that all the voltage is transferred. So there we go, we put it in between two subsystems. So now we've got a high input impedance here, so we get maximum voltage transferred into here, and then we have this one is now a low impedance, and that one's high, so then we get maximum voltage transferred from there to there. So whereas normally you'd have lost some, with that in the middle, you end up making sure you keep all the voltage. But again, as I said, you only really need to know the circuit for that. It's not to ask about too much. Okay. The other thing you need to know about these is if you're making a preamp, you might need a lot of gain, because a microphone signal can be very weak, or something like a guitar pickup. The problem is with gain, as you increase the gain of an amplifier, and generally we're talking operational amplifiers are used for preamps, as we increase the gain, the bandwidth will decrease, because they're inversely proportional, because you've got gain bandwidth product equals gain times bandwidth. So if gain goes up, the bandwidth goes down. Problem is, if we want to make it suitable for music, we've got to have the full audio range up to the limit of human hearing, or it won't sound good. So we need 20 kilohertz bandwidth. If we've got a gain bandwidth product, set means that we can't get more than a gain of 50 if we have a bandwidth of 20 kilohertz. Then if we want to increase that, we can multi-stage it. Now we'd have a 50 times a 50, they multiply together, so they'll actually give us a gain of 2,500 with a bandwidth of 20 kilohertz. So we can chain them up as a multi-stage amplifier. And that gets around the bandwidth problem. So this wouldn't be a good idea, because now we've got a 25 times amplifier and 100, it gives you the same overall gain, but the problem is we're letting a full range of 40 kilohertz through this one, but then this amplifier is cutting it right back down to 10. So we only get the worst possible scenario there. So therefore the overall bandwidth of this amplifier will be 10 kilohertz with a gain of 2,500. So the moral of the story is...
Why did you pick the end one then?
Sorry?
The bandwidth, why is it 10?
Well, because bandwidth is the range of frequencies that the amplifier will amplify. And then if you're going to pass to another one and that's cut off everything above 10 kilohertz, you can never get that back. Once it's lost, that information is lost for good. So you could have like a bandwidth here of 100 kilohertz and a bandwidth here of 1 kilohertz, and you'd only ever get 1 kilohertz through. It's a bit like a filter or something.
So is the bandwidth overall always the end one?
No, it's just the worst.
It's the worst one.
So if that was 10 kilohertz here and that was 40 kilohertz there, the bandwidth would be still 10 kilohertz. Because you've lost everything above 10. Yeah, you're passing it to the next stage. It's gone already. You can't get it back. It doesn't matter which way around. It's just the worst. So therefore, you need to have, like that, two identical amps with the same gain multiplied together gives you the maximum possible bandwidth. The other thing you need between them is a decoupling capacitor, sometimes called DC blocking capacitors. DC doesn't go through capacitors, and they allow AC signals through, but they block DC. So you just put little capacitors between each stage of the amplifier. Because if you have, even if you have something like 0.1 of a volt DC present on the input there, if you've got a gain of 10, then you're going to have 1 volt here. And if that goes through a gain of 10, you'd end up with 10 volts there. So what we need to do is make sure that all the DC part of the signal is gone, otherwise the amp will stop working properly. You need to get rid of any DC signals. You always get DC lurking around when you don't want it in amplifiers, so that's what the capacitors do to get rid of that. Okay. Then we get onto the mixer, which is effectively a summing amplifier with as many inputs as you want, based on an inverting op amp. Doesn't work with a non-inverting, so it's always an inverting one like that. And we can get the gain, it's given on your data sheet from these, is get the output as minus RF divided by V1 over R1 plus V2 over R2 plus V3 over R3 and continue. That form is on your data sheet. The way to think about it though, I think, is really the gain on each individual channel is equal to minus RF over Rin for that one, RF over Rin for that one, RF for Rin over that one. You just add all the signals together. That's effectively what that formula is doing. Okay? So it adds signals together. So you have microphone, drums, guitar, it adds them together. That means that it keeps adding them up. You can quite easily saturate the amp. So the gain on these is quite low to stop it giving too high an output. And we also need to control the volume of each channel. So we put a variable resistor there, which are the faders on a mixing desk to bring the level up and down. The input impedance of them is, when these are faded right up, means that these would be at 0 ohms, and when it's faded right down, so you can't hear it, these would be much higher resistance. These are the minimum input impedances of the amp, and you need to add that and that together to get the gain. For each channel, the gain is minus RF divided by that and that added together. And obviously the variable resistor can change from 0 ohms up to whatever it says on it. So they can get some tricky little questions around that. So for instance here we've got the maximum gain is going to be minus 30 over 20, so it's going to be minus 1.5, isn't it? Okay. The minimum gain when it's fully faded is going to be 30 divided by 120 for that channel. Okay? You can do the same for each of the different ones. Okay, so you kind of have these two. So that can be anywhere between 0 and 100. That means the minimum input impedance on this channel is 20k, 10k and 10k there. Sometimes they specify the input impedance you need.
So do you not count the variable resistor when working it out? Or what do you do when it tells you?
Yeah, it'll tell you, usually consider it's either 0 or 100, or it'll tell you a value. Depends on the question. It's all generalising. You might want to dig out some more questions on it. Yeah, mixer sums input voltage. As a result, it's easy to drive the output into saturation, so that's why, as I said before, the gains are kept quite low. You don't want it to distort. Then we get on to tone controls, where these are effectively active tone controls. So this means they can boost as well as cut. So that means the gain can be above 1, whereas the passive ones can only have a possible maximum gain of 1. And so we have 4 different types of filters. The way to remember them is, he said bass first. You need the bass, the lower frequencies, to have the part of the graph that's at an angle. So that's bass boost because it's getting higher. That's bass cut. Treble, so at high frequencies are boosted there and cut there. The gain of the level areas of it, you can calculate just from the circuit using the resistor values. So we'll go through each one. We need to work out the break frequency. The point where the filter kicks in is used using the capacitor and the resistor, the ones that are next to each other. So for instance, we've got C, break frequency is equal to 1 over 2 pi RC. So in this case, that'll give a break frequency of 169.3 Hertz. Then we need to learn which circuit gives which type of filter. So they're all the same kind of idea. We move the filtery bit from here to here, and we put them in series and we put them in parallel depending on which type it is. To work out the gain at the flat bit, you just do minus RF over Rin, like you would do for any other op amp.
Doesn't that give you minus gain?
Yeah, they don't really. Doesn't matter particularly. It will give you minus gain, yeah. But they don't plot it as minus on the graph. So base boost, we have the capacitor in series with the resistor on the feedback loop. And that means that base signals, low frequencies, are getting blocked by that capacitor from coming back round the negative feedback loop, which has the effect of the low frequencies have not being reduced as much by the negative feedback. So the low frequencies are boosted because they're not getting back through the feedback loop. Okay, so that gives you base boost. And then you've got base cut, we just move it to the input. Now low frequencies can't get through the capacitor, high frequencies can, so this reduces the base. So by swapping them over, you've got base boost, base cut, base boost, base cut. And then treble ones are the ones that are in parallel. You've got treble boost. The high frequencies can skip around this resistor here, through there, and get extra boosted. If we put it on the feedback loop, the high frequencies now can skip around the resistor here and get extra reduced by the negative feedback. So that cuts the treble. So you just have to try and find a way of remembering those. Remember treble parallel, base serial. Okay, so we tend to have log paper on these. So that's got a break frequency of 2000, and that's a gain there of 1, 2, 3, 4, 5, 6. So sometimes you might be asked to design a filter by rearranging the break frequency formula, choosing a capacitor, then calculating what resistor value it would be. That's obviously a treble boost. So you'd work out the value for the resistor by rearranging the formula, and then you go back to saying, well, that's treble boost, so it'd be that design there, with that capacitor in whichever resistor you calculate. Okay, final bit really is the power amplifier. Then this bit is the bit where we really need to transfer power. Beforehand we transferred voltage, but that won't drive a speaker on its own. The speaker needs power. To have power, you need voltage and current. So therefore, we need to transfer the maximum amount of power from the amplifier to the speaker. The problem with that is it isn't as simple as you'd think. To make it most efficient, the power transferred from one subsystem here, the power amplifier, to the loudspeaker is at a maximum when the input resistance of B is equal to the output resistance of A. So those two values need to be the same. That's why when you buy an amplifier, let's say it's an 8 ohm output, so you buy speakers that are 8 ohm to match it. Okay? That makes sure that the maximum amount of power is transferred. It's still only 50% efficient though, because you've lost half the voltage. If that is, say, 1k and that is 1k, it's like a potential divider. The voltage here is going to be half of what the voltage is there. So that's why power amplifiers always have big heat sinks in them to get rid of the heat that's produced in them. So only half the power actually ends up in the loudspeaker. And we did that thing about adding speakers in parallel and series, if you remember, in a car. You can't do anything. You try and increase the impedance of the speaker, then you'll end up with less power transferred, and if you then reduce the impedance of the speakers, you get less as well. So the maximum is reached when the two are matched. And then we're looking at different types of power amplifier. The simplest is the emitter follower, which we've seen before, which is just a transistor. We connect a speaker here. It's often used in projects and so on. This we've got a 0.7 volt drop. Literally, the formula is just voltage out is 0.7 volts less than voltage in. But we have a much bigger increase in the current down here. A little current there will be increased by HFE, which is the gain of the transistor, to make a bigger current through there. So even though you've lost 0.7 volts, overall you get a lot more power. Problem with this one is it'll only amplify positive voltages, so you'd lose all the negative part of the cycle and 0.7 volts of the positive side, so you just end up with that, which sounds awful. So they'd only be any good for like alarm sounds or something that doesn't matter, any good for music particularly. So what we can do is we can bias the transistor by using a potential divider there to raise this voltage up, use a blocking capacitor there, apply an AC signal to this, and it will add half the power supply to it, lifting it up like that, which means it's always positive. We still lose 0.7 volts, but now you get the whole signal. But it's wasteful because the transistor's on all the time, so even when there's no music playing, it would still use power and there'd be current going through the speaker, so it's not efficient. So we can go one better. We could use a PNP transistor, which would just amplify the negative part of the cycle, but that doesn't get us anywhere. So if we really want to do it, we can use the push-pull amplifier, which has an NPN transistor here and a PNP transistor there. So when it's a positive signal, you get positive voltage here, triggers this, current through there, powers the speaker. When you have a negative voltage here, then effectively it will pull current from 0 volts out and down to here. So we've got it, that one pushing and that one pulling the current. So you get both the positive and the negative parts of the cycle done. But you still have a problem in that we get something called crossover distortion. You put in a sine wave like that, the output has this bit here where it's flat, where between minus 0.7 and plus 0.7 volts on the input, the amp will be dead because of the transistor's voltage threshold. So we need to know that little shape there. Let's draw crossover distortion. And there it is on an oscilloscope. You can see the blue line is the original signal, the output is the yellow one. We've lost 0.7 volts and there's the crossover distortion. So we can bias the transistors using diodes to add 0.7 volts back on and take away 0.7 volts, the negative part of the cycle. So it kind of moves the positive voltage up and the negative voltage down slightly. Then that gets put back again here by the transistor taking the 0.7 volts off again, and it kind of compensates for that. So adding the two diodes, you need to know that circuit. NPN transistor at the top, PNP transistor at the bottom, and the speaker. You get rid of the crossover distortion. And then finally, to calculate how much power you can get out of an amplifier like that, it's the power supply voltage from rail to rail. So if it's plus 12 volts and minus 12 volts power, that would be 24 squared divided by 8 times the load of the speaker, 8 times Rn. Okay? So if you've got you need to make sure you don't fall for if it's plus 12 and minus 12.
We get that equation.
Yeah.
Well, so if it's plus 12 and minus 12, it'd be 24.
Yeah, it's 24 because it's the rail to rail voltage rather than the.
Right, okay, yeah.
That's what gets people on that one. That's it. Straightforward. That's it. Power supplies. Not power supplies. Audio systems.